Like the cellular technologies of 2G, 3G, 4G and now 5G, Wi-Fi has also evolved over the past 20 years or so to enable us to send data at ever faster rates and to support our unquenchable thirst to access the internet. However, behind the general term Wi-Fi is a set of technological standards from the IEEE, the Institute of Electrical and Electronic Engineers, named 802.11. In this video, we're going to focus on one of these standards, 802.11ax, which is now more commonly referred to as Wi-Fi 6. Introduced in 2021, Wi-Fi 6 set about improving the efficiency of the network rather than just focusing on increasing the data rates, although it does manage to achieve that as well. On the diagram, we have highlighted several of the key characteristics that define Wi-Fi 6 in terms of the frequency band, channel bandwidth, and access technology. Beginning with the frequency band, it is important to note that Wi-Fi 6 can support a new ISM or Industrial, Scientific and Medical band at 6 GHz, in addition to the more standard frequency bands of 2.4 GHz and 5 GHz. We shall review this in a little more detail in just a moment. Furthermore, like that of Wi-Fi 5, Wi-Fi 6 is also able to support channel bandwidths of up to 160 MHz and multi-user MIMO. However, this can now support up to 8 streams in both the uplink and downlink directions. One of the most important changes introduced by Wi-Fi 6 was support for a more efficient access methodology, OFDMA, or Orthogonal Frequency Division Multiple Access. Interestingly, OFDMA is also used in 4G and 5G cellular networks, although it should be noted there are significant differences. Once again, we shall return to discuss this later in the video. Finally, in terms of Wi-Fi 6 characteristics, a new higher order modulation technique has been introduced, 1024 QAM, and thus each of the different 1024 states the radio wave can exist in represents 10 bits, a 25% improvement upon Wi-Fi 5. As such, this, in addition to the wide channel bandwidths, the MIMO streams, enables Wi-Fi 6 to support a peak physical layer data rate of 9.6 gigabits per second, or more realistically, an effective data rate of 6.25 gigabits per second. Referred to as Wi-Fi 6E, this terminology is used to describe the capability of a Wi-Fi 6 device to operate in the new 6 GHz ISM frequency band, i.e. between 5.925 GHz and 7.125 GHz. It should be noted, however, that in different countries throughout the world, not all this radio spectrum is available for use, with some countries limiting the 6 GHz band to a 500 MHz wide band allocation up to 6.425 GHz. Compared with the legacy frequency bands of 2.4 GHz and 5 GHz, the new 6 GHz band can support significantly more channels, as illustrated in the diagram. These range from 59 20 MHz channels up to 7 160 MHz wide channels, although this will not increase the achievable data rates over and above Wi-Fi 5. It does significantly improve radio planning by reducing the probability of neighbouring access points using the same channel. The second characteristic we're going to address is Wi-Fi 6's capability to support up to 8 MIMO streams on both the uplink and downlink in a multi-user configuration. Therefore, in theory, a single access point could support a bidirectional link with up to 8 different Wi-Fi stations simultaneously by placing each on a unique MIMO stream. However, it is important to appreciate that multi-user MIMO requires spatial diversity for optimal performance. That is, in an ideal world, the 8 Wi-Fi stations should be evenly distributed around the antennas of the access point, something which in reality may be difficult to actually achieve. The third and final characteristic we're going to focus on in this video is Wi-Fi 6's ability to use OFDMA as an access methodology. To begin with, however, we should first of all recap how Wi-Fi 4 and Wi-Fi 5 utilises OFDM. The diagram illustrates how a 20 MHz wide channel is subdivided into 256 subcarriers. However, all of these subcarriers will be utilised by a single Wi-Fi station at the same time. In fact, even with multi-user MIMO, the multiple Wi-Fi stations will still use all of the subcarriers, but be separated by the fact that they are operating on spatially diverse streams. Switching to OFDMA sees these 256 subcarriers being grouped into RUs, or resource units. And it is these resource units which can be allocated to different Wi-Fi stations. Note, the resource units can either be grouped into blocks of 26 subcarriers, or if higher data rates need to be supported, blocks of 52, 106 or 242 subcarriers, the latter effectively allocating the entire channel to a single device. Wi-Fi 6 can support channel bandwidths of not only 20 MHz wide, but also 40 MHz, 80 MHz and 160 MHz. And as such, depending upon the specific allocation, resource units containing even more subcarriers can be supported. For example, a 160 MHz wide channel can support either 74 resource units comprising of 26 subcarriers, or a single resource unit comprising of 1,992 subcarriers, or as they can also be referred to as tones. So, pulling all of this together, the question that arises is, how does this make Wi-Fi 6 a more efficient technology? Well, let us consider a Wi-Fi network using OFDM, namely Wi-Fi 4 or Wi-Fi 5. Here, assuming we are not considering multi-user MIMO, the network is only capable of supporting a single device at any time. And as such, assuming the devices have limited data to send, there is significant wasted spectrum. However, in the case of Wi-Fi 6, which supports OFDMA, it is possible to allocate the resource units to different devices, such that all the available resource can be used. That is, multiple Wi-Fi devices will be operating on different subcarriers, and therefore in different parts of the channel. Furthermore, OFDMA and multi-user MIMO can combine, making Wi-Fi 6 even more spectrally efficient.